Okay, so team, good morning.
Good morning.
Okay, so did you get a chance to go over all the problems we have covered till now on dynamic programming? And do you have any questions regarding how to proceed solving dynamic programming problems? Any questions so far? See, two most important steps of dynamic programming problems, right, are coming up with a subproblem and then coming up with a recurrence. To find a recurrence, you need to come up with a subproblem. That subproblem, right, you will get to know from a lot of practice. So typically it will be of the form C, A of I, B of ij, C of ijk, so on. And what are these ijk? So the problems might have different parameters, right? In Fibonacci, the only parameter was the ith number. In the tiling problem, we had a 2 cross I board, right? See, only one parameter. And then we have a couple of problems where we see two parameters. So typically when you are dealing with two strings, right, you have to scan one string using I, you have to scan another string using J. So that's a two parameter problem. Or in knapsack, we will see that one parameter is used to scan the items. Another parameter is used to scan the weights, right? So yeah, it depends on the problem. What are the parameters given in the problem? And so what is this? IJK. Maybe in a problem like Floyd-Warshall, IJK can mean, so I comma, so okay, from ith node to jth node, right? Considering all nodes up till k, something like that, right? So it is problem dependent. So three parameters. Okay, now you might ask, do we have only one way to formulate a dynamic programming solution or algorithm given a problem? Need not be. There can be multiple ways of formulating dynamic programming solutions. Okay, it need not be one. So one of the best examples is egg dropping puzzle, right? When you encounter puzzle like this, egg dropping, so we will not cover it here, but you can find it on the slides and also a lot of material online. I don't know whether the websites cover that, but it has been covered in the book, right? Our puzzle book. There are different ways to write DPs for the same problem. So one dynamic programming formulation tries to find the number of drops using one formulation. Another DP formulation tries to minimize the number of flows. So it is written in a slightly different way, right? So it is possible to have multiple DP formulations for the same problem. Okay, both of these might get you polynomial time solutions. But again, if there are multiple DP formulations, your aim is to reduce time further, right? Among two polynomial time solutions, of course, you will choose the smaller one, right? Anyway, so for a lot of problems that we are seeing now, so for example, Fibonacci, it seems like there is only one formulation, right? I mean, we cannot think about any other second type of formulating DP for it, right? So yeah, like most of these problems, you don't need to worry. So we can consider this as the only type. I don't know if there are other types, but we can consider these are the only types. But there are some more where there can be multiple DP formulations. Okay, you don't need to worry about multiple DP formulations, but this is just for information. Okay. Next. So this is the way you need to come up with subproblems. And how do you get to know? When you solve maybe 7 or 8 problems related to strings, where you're dealing with 2 strings, you will see that this is often the subproblem. That is, I, right, means the ith character of the first string, or it can mean the first I characters of the first string. J can mean the first J characters of the second string, right? When you're dealing with 2 strings. In knapsack, I can mean the first I items. J can mean the first J weights or max J weight, something like that, right? It is problem dependent. But with more practice, you will get a hold on how to come up with subproblems. Okay. So that's regarding subproblems. So your step 2 after understanding the problem should be coming up with the subproblem, right? Do not worry about the recurrence. Do not worry about the algorithm. Come up with a subproblem. Okay, that is step 2. Step 3. Now think about the recursive formulation. That is, so you have your subproblem, maybe say B of I comma J or whatever. How do you find the recursive relationship? I will give you a clue here, hint here. I don't know if there is a better way to say this. So try to check, right, or analyze if there is a relationship of this cell with its neighboring cells. Neighbors. So what are the neighbors? Maybe I of, let's say, I minus 1, J. Maybe I of, sorry, B of I comma J minus 1. Maybe this I minus 1, J minus 1. And so on. There can be more, right? I mean, you can also write it like this, I minus 2, J minus 2, and so on. But you will see that for many problems, this is not the case. So typically, the neighbors for most problems, B of ij, depend on these 3 neighbors. Maybe 2 of these 3 neighbors. Now, your goal is to rigorously analyze what is the dependency of this cell, right, on other cells. And as I said that in most problems, it will be neighbors. This is not always the case, but for most problems, this idea, this direction, this heuristic works, right? It simplifies problem solving. Okay, so similarly, if you're dealing with f of I, you check the dependency of this with neighbors. And you know why this is true, right? For Fibonacci, this worked. F of I depends on I minus 1, I minus 2. And we saw one more problem, right? Let's say compositions problem. F of I depends on I minus 1, I minus 3, I minus 4, right? Kind of neighbors. Okay, what else? We also looked at a tiling problem. So there also, C of I is C of I minus 1 plus I minus 2 neighbors, right? This seems like a fantastic heuristic to attack a lot of DP problems, right? So you already saw how to come up with subproblems, right? Some heuristics on that. For recurrences, typically, right, when you solve more than 50 problems, you will realize that, okay, these are not that difficult. You majorly need to analyze each and every neighbor. That will give you a pretty good hint on what are the read cells for this write cell? This is the cell that is returned to, right? Right. You are writing on this. When you're writing on this, what are the other cells it reads from, right? Typically, they will be the neighbors. Make sense? Okay, let's continue. So with this, the more you practice, you will see the pattern more clearly, and you can easily attack more new dynamic programming problems. Okay. So let's start with this. Count paths in a grid. Now you have a grid, a rectangular grid. So what is the aim? Our aim is to count all paths from the top left corner, say 0, 0, right? Maybe here, to bottom right corner, m, n, m, n, 0, 0 to m, n. Okay, what are the constraints? The constraints is that you can only go right or down. That's it, right? You cannot go left from any cell. You cannot go up from any cell. You can only go right ways or down ways, right? So find all the, or count all possible paths. See, this is one possible path, right? Right, and then down, 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 down. Maybe this is one possible path. See? This is one possible path. So here it is down, then right, down, so on. So how do you count all possible paths? So how do you proceed from here? I mean, leave DP, dynamic programming. So how would you normally solve this problem? Any idea?
You need to make a move and then see if there's a how do I say what I'm thinking? Look at the neighbors to see if they even exist. So what I'm saying, like in the first one that you drew, keep going right until you can't go right anymore.
Mm-hmm.
And then go down. Like same thing with the next one, right? You can go right or left, so randomly choose one. You could go right or left, right or down, sorry, randomly choose one and do that until you don't have any more options.
Mm-hmm. Right. So you want to do it in a random fashion?
I guess that's one option.
Yes, that is one option, definitely. Very good. Next. Other ideas?
Can't you just multiply m and n together? Because in order to get from origin to m comma n, you need to go down m times and to the right, or you need to go down n times and right m times, which means you have to make m total right moves and n total down moves. And so it's just whatever combination of that you choose, so m times n.
Very good. Okay, let's do that. So let's try to solve it for maybe 2 cross 2. Will that work? So let's see. So how many possible moves are there maybe in this diagram? 0, comma, or should we take a simpler example? So does that always work? Is the question.
It probably will not work.
Okay, let's choose this. This is one path. This is another path. This is the third path, right? Only 3 paths possible here.
Mm-hmm.
And m comma n is what?
3.
How many nodes you have? You have 6, right?
Yeah, but starting from it would probably there would have to be a +1 in there somewhere.
Well,
okay, so try it for other examples. Will it still hold? Excuse me. Will it still hold? Okay, so I mean, so how did you find this formula? M cross N.
So in order to go from 0 to mn,
Mm-hmm.
you need to go down n times in order for that
Okay.
to work.
Right.
And then you need to go m to the right however many times. So it's just some combination of, m rights and n downs in any particular order that you need to do in order to get to the final point.
I see. So to analyze it, what if we say this, right?
I, I'm sorry. I think there is a defect of that. Consider the 2 by 2, right? You have two possibility, but for your formula, that's 1 times 1, it's 1.
Yeah, which is why I think there needs to be a +1 in there somewhere.
Yeah. So what I'm thinking about is actually, if we move from m minus 1, n minus 1 to m n, then how many possibility you have? You have just 2.
Mhm.
And if you from m minus 1 to mn, you have 1. And from m minus 1n to mn, you have 1. So you have probably 2 times m minus 1, n minus 1 plus m minus 1n plus n minus 1. I think that's probably the formula.
I see. So try to find different ways to attack this problem, right?
Mm-hmm.
So okay, so let me give you one idea here. Check whether that works or not.
Okay.
So the first claim, I mean, I can make a small change. I don't know whether you want to consider 1, 1 here or 0, 0. I mean, that can be fixed later. Okay, not a big deal. So see, every path is of size m plus n. Is this correct?
Yes.
Is this correct? Every path is of size m plus n.
Yes.
Do you agree?
Yeah, yes.
Okay, fine. So in each of these paths, you need to make sure that there are m right moves. Do you agree?
Yes.
Yes.
Right? There will be m right moves and n. We considered this as m, right? And this as n. Okay, so we can say m down moves and n right moves. Okay. So in each path, you should have m down moves and n right moves, correct?
Yep.
So what you can say is in all strings of length m plus n, right? Find the number of ways in which you can write these strings such that you have m down arrows. Make sense? Can we say this?
Can you say that one more time?
So each path is a collection of down, right, right,
Combination.
right,
Yeah.
combination. And the size of this is m plus n, correct?
Yes.
And in this path, there should be m down arrows and n right arrows.
Mm-hmm.
A valid path, right?
Yeah.
Okay. Now try to find construct all possible paths, right? Of size m plus n, right? Construct paths of size m plus n such that there should be m down arrows.
Yes.
So this is the meaning of the number of ways in which you can choose m items out of m plus n items.
Yes.
Is this correct?
Yes.
Yes.
This is equals, yeah, I mean equal to m plus n c n.
Yes.
Yes.
I mean you can solve it via this or this because both are same. So does this work? So this is combinations. Choose m out of m plus n. In how many ways can you choose m out of m plus n items? In how many ways you can choose m down arrows, right? In a path of m plus n down and right arrows. Make sense?
Yeah.
See, you can also think about okay, let's consider a right move as 1 and down move as 0. So consider all possible bit strings of size m plus n, correct? Bit strings of size m plus n. In how many ways, right, you can construct bit strings of size m plus n such that they have, say, n ones. It's this, right? Which is same as in how many ways can you construct bit strings that have m zeros? Same. N ones is same as m zeros. Correct?
N1 is the same as M zeros. Yes.
So try whether this idea works. Okay. Anyway, so that is algorithmic solving, right? Okay, so that's fine. So here we will see dynamic programming formulation. I mean, that can be a closed form solution, but you know, for every problem, you cannot come up with a closed form solution. Fibonacci also has a closed form solution, but you know, if you look at the proof, that is slightly complicated, right? So you cannot come up with closed form solution to every problem out there. Hence, dynamic programming is much more generic strategy. Okay. Fine, let's start with this problem. I mean, we will see this in terms of TP. Subproblem. What is a subproblem? As I said, parameters. Ij, C of Ij. Let C of Ij represent the number of paths to reach the cell Ij from 0, 0 using right arrows and down arrows only. Okay, so you want to compute C of Mn. Is this clear? That means we are really filling a table. So each cell computes the number of paths till that point, right? With all these constraints, starting from 0 to this cell, the number of paths. So you will.
So Professor, can I just ask a question here?
Yes.
So for this one, the goal, wouldn't the goal just be the total number of paths and not the like is C of Mn? That's the different combinations of M plus N, but wouldn't we want the goal to be a total sum of those?
So C of Mn is all possible paths from 0, 0.
Oh, okay.
Mn.
All right. Okay.
It automatically includes all paths.
Okay. All right. I got you. Thank you.
Right. But okay, what is C of 2, 5? So consider 2, 5 as a cell, right? So you want to compute all possible paths from 0 to 2, 5.
I see.
So for every cell you compute this number of paths to reach that particular point.
Okay.
That is the subproblem.
Okay.
Right? Okay. Now the subproblem is clear. Here is your recurrence. So take a look at this. Spend say 20-30 seconds And now tell me, why is this correct? Or if it is not correct, why it is not correct?
Why I equal to 0 and j equal to 0, it's 1. It should be 0, right? Is it?
Oh, I see, I see. Let's do one thing. We will come to the base case later. Okay. So let's always first come up with the recursive solution, right? Look at the recursive case, and we will think about the base case later. Just focus on the recursive case right now. And let me introduce one term here. See, you're seeing a box, a colored box, right? That is called I-version bracket. I-version bracket. And what does it represent? So typically that bracket, I mean, typically we write something like this. Condition, the square brackets, but if we use square brackets, it's confusing, right? We are also using square brackets for arrays and all that stuff. Actual I-version bracket uses these square brackets, but here I have replaced it with a colored box, right? So that means colored box for a condition means that replace that box with 1 if condition is true. Condition is true, right? Replace that box with 0 if condition is false. Make sense?
Okay.
If that condition is correct, replace it with 1. If that condition is false, replace it with 0. And that condition depends on the value of j.
I cannot hear anything wrong.
Okay. So now let's think about how we get this. Can you tell me how we get this? So here we are saying that ij depends on ij minus 1, ij depends on I minus 1j. And we need to add them up. Why? Why? So let's consider a diagram, right? Maybe that will simplify stuff. Okay, so let's consider a diagram. So as I said, the generic subproblem is this. You should always consider I comma j, right? Right. Okay, so you want to compute all possible paths that reaches I comma j, correct?
Yes.
Now, let's consider these cells. What is this cell? This is I minus 1j, and this is ij minus 1, correct? So this is your I increasing, j increasing. Make sense?
Yes.
Okay. Now look at the beauty of this. Every path that reaches I comma j, either it should come from here or it should come from here. That's it.
Yes. Yes.
Do you agree?
Yes.
So now let me erase this and rewrite this again. See, it should come from here or it should come from here. It cannot come from anywhere else, right? Suppose the number of paths that reaches this cell is say 100, the number of paths that reaches this cell is 200. Can you tell me what is the total number of paths that reaches I comma j here?
300. We have to add them both together.
Just add them both. And why should we add them both? I mean, can't there be common paths that reached both these 100 and 200? What if there are, 50 of these paths are common?
How can they be common if they end up at different spots?
Very good. So they cannot be common because they end up at different cells. So there is absolutely no common path. So they are independent paths. Hence, we can add them, right, without any problems. So the total number of paths at I comma j is now 300 for this example. In general, if the number of paths at this is C of I minus 1j, number of paths here is C of ij minus 1, number of paths here will be C of I. Okay, so I will just write it as sum of these two, right? Sum of these two, I minus 1 and ij minus 1, I minus 1j and ij minus 1. Do you agree?
Yes.
That's it.
Yes.
That's it. Done. And why do we have that I-version bracket and all? I mean, suppose this does not exist, right? For example, if I comma j is here, suppose this is a 0 comma 10. Now, can you have 0 minus 1? There is no cell here, right?
Right.
But there is a cell here. Correct? There is a cell here.
Yes.
So, j greater than 1 will be 1 here, and I greater than 1 will be 0 here. Hence, this value will not be added. Make sense? So does this make sense?
Well, it makes sense when someone lays it out. It's another thing to come up with it on our own.
Right. Correct. But see, it's important you understand the recursive case, right? It's very important you understand the recursive case. So first we got these two, right? We got these two. And then we said that, okay, so j minus 1 should be greater than or equal to 1. See, if it is, if j itself is 0, what happens? This will be minus 1. Minus 1, I mean, it's not an index in the array, right? Similarly, I minus 1, I should be greater than or equal to 1. If I is equal to 0, it's not an index, right? Hence, we are making sure that we are accessing proper values here. And then you add them up. So if I is in the range 1 to m or j is in the range 1 to n, you can use this formula. And I is equal to 0, j is equal to 0, and means what? It's the first cell, 0, 0. It is 1. Right? I mean, assume that the number of ways to reach it is 1, just 1. Make sense? See, if this is 0, if you cannot reach this, what happens then? If you cannot reach this, you cannot reach any of the other cells, right? Hence, this has to be 1. The starting cell is reachable. Yes, it is reachable. The total number of paths is 1. So does this make sense?
Yes.
Okay, now let's take an example and we will come back to the algorithm and all later. So here is your dependency. Okay, we will look at the dependency and then the example. I comma j cell here depends on, this is I minus 1j and I j minus 1. Okay, here I comma j depends on I j minus 1, and this cell is not present because
There's nothing above it.
I is equal to 0 here, right? I starts from 0, I is equal to 1, I is equal to 2, so on. So I should be at least 1, right? For it to access the above part. Similarly, j is equal to 0, j is equal to 1, j is equal to 2, so on, right? So here there is no cell to its left, hence that cell will be 0. Make sense? And this one, the count should be 1. The base case is if I is equal to 0 and j is equal to 0, the count is 1 here because it is reachable. The starting point itself should be reachable. Now let's look at this example. Oh. Right, see here, the starting cell is reachable. From this cell, you can always reach this point, right? From this cell, you can reach this point, this point. So each of these will be 1 because there is no cell above this, right? There is nothing here above this. So all these cells will be 1. Similarly, all these cells will be 1. Okay, now look at this, say this cell. The number of ways to reach C2, 4 is 15. Number of ways to reach 3, 3 is 20. You add these two, 20 plus 15, you get 35. Why? Consider all paths to reach 20, right? So you can add one more right arrow to reach this cell, 3, 4. Similarly, all paths to reach this cell, 2, 4, add a down arrow here, you can also reach 3, 4. Make sense? That is the idea behind dynamic programming. That means you're reusing the existing solutions, right? You won't be recomputing them again and again and again. Right? So here is your pseudocode. So instead of just initializing only one cell, what you can do is you can initialize the entire row, entire column, right? I mean, that is a bit faster because you know from the diagram that it's only one possible path to reach any cell at the 0th row or the 0th column, right? Hence, you can initialize this. And later, for I greater than or equal to 1 and j greater than or equal to 1, that is 1 to m, 1 to n, just use this loop. Okay? Make sense? Simple, right? Questions? Okay, complexity mn, because we used mn everywhere, right? Next, let's change the problem slightly. Suppose you have blockages here. Some cells are blocked. I mean, you can see this when you want to see a ball drop in New York City, right, on December 31. Every year, some roads will be blocked. You cannot pass through those points. So that's the exact same idea here, right? Some cells are blocked. You want to find the total number of paths from 0, 0 to m, n with right and down moves. Exact same problem, But you should also consider the blockages. Here you cannot pass through this point. That means total number of paths that reaches this point is 0. Right? Okay, in that case, how do you solve the problem? Can you reuse the solution of, right, like what we got and extend it slightly, or should we come up with a completely new solution? See, in DP, right, it's so beautiful that when the problem generalizes, you can also generalize the recurrences. Now think about the formula. We came up with a formula, right? M plus n choose m, or m plus n choose n. We used a nice idea to come up with that formula, but think about, can you generalize that formula here? Can you tweak that formula here? No. It's very tough, right? You need to come up with a very different way of thinking. So often what happens is when you come up with a lot of variants, a lot of these techniques fail. And it's not easy to easily generalize or modify those techniques to work on, right, other variants. On the other hand, DP, right, in many cases, when you tweak the problem, when you consider variants or generalizations, the recurrences can also be generalized or, slightly tweaked or modified. That means you can reuse the existing recurrences. Right? That's the beauty of DP. Let's see. So the input, see, input should also change. What is the input? Now you should get another matrix as input. Consider this O matrix, where O of ij means if it is open, if it is 1, O of ij is 1, means there is no block. That cell is open to pass through. If it is 0, that means there is a blockage. You cannot pass through. Right? That is also an input to this problem, right? We need to know that. Okay, now the subproblem remains the same. Paths to reach this, assuming we have all these blockages, right? Assuming we have all these blockages. So it's the same. What is the recurrence? So look at the beauty of this solution. You just need to multiply each term by O of ij. Done. Problem solved. Now, can you tell me why should we multiply each term by O of ij, and what does that mean? What does that mean?
Because if O of ij happens to have a 0 in it, meaning it's closed, then that path will be removed from the sum.
Right. So if it is 0, that cell is blocked. If that cell is blocked, the number of paths to reach that cell must be 0. So multiply that by 0. Okay, if the cell is open, that means you can have paths coming into it, right? Then directly apply the recurrence we already had. The same ideas apply, so the same recurrence applies, right? If it is an open cell, the same recurrence applies. If it is closed, only then you consider that as 0. So multiply that by 0. Done. Problem solved. There is nothing else to be done here, right? Though it looks like a tough variant to solve, but what we did is just multiplying that with the information that whether the cell is open or closed. Done. Beautiful, right? So like this, there are a lot of DPs where when you generalize the problem, the recurrences can also be modified slightly, not a lot, slightly, to get solutions to those generalized problems. But think about the other techniques, choosing and all we discussed, right? It's not easy. It's not easy to generalize because it depends. See, it does not depend only on the blockages, probably. It depends on the positions of the blockages, not just the number of blockages, right? Make sense? So if you have, say, two blockages, those two blockages are at the end points, so that can give you a different number. If those two blockages are just before the destination, that has a different concept, right? So like those formulas might not consider all these positions and all. So it's probably not easy to come up with an easy solution generalizing those formulas, because the positions of blockages matter, not just the number. The positions matter. Of course, the number, total number also matters. Make sense? Number as well as positions. Anyway, so that's your recurrence. The dependency will remain the same, right? Algorithm, what's the change? Just multiply by that O of ij cell everywhere. Done. Right? See, here the input also includes the O matrix, and everything else remains the same. Complexity also remains the same. Okay, next, binomial coefficient. Do you know about binomial coefficient? So let me give you a very brief idea. So this is the binomial coefficient. N choose R. N choose R. So it is written like this, or it is written like this, N choose R. N, C for choose, N choose R, or it is also written like this, N choose R. Okay, what do you mean by N choose R? The total number of ways of choosing R items from a set of N items. From a set of N items. The number of ways of choosing R items from a set of N items. You can also define it as the number of ways of creating R-sized subsets from N elements, right? R-sized subsets. So how many 10-sized subsets are there from numbers 1 to 100? 100 choose 10. Make sense? So you can also consider this as the number of ways of choosing n-bit strings such that R of them have ones, or you can say R of them have zeros, whatever, right? Number of ways of choosing n-bit strings, or number of n-bit strings where R bits are ones or R bits are zeros. Make sense? And yeah, do we have any other ways to define it? Okay, maybe there are many more, right? Many more, but the meaning of n choose R is something like this. And there is a formula also. And what is that formula? N choose R is equal to n factorial divided by R factorial n minus R factorial. Okay, remember this formula. N factorial divided by R factorial times n minus R factorial. So there is a recursive relationship also So this is n minus 1 CR plus n minus 1 CR minus 1, right? N choose R is equal to n minus 1 choose R plus n minus 1 choose R minus 1. So n minus 1 appears on both sides here. And then this is R minus 1. Okay. Next. Right. So why do we have this? Okay, this is another way to consider all these coefficients. Now consider this, x plus y whole power 1 is equal to, can you tell me, like, what is the result?
X squared plus 2xy plus y squared. Oh,
okay.
to the 1. Sorry, to the
One.
1. Sorry. It just x plus 1.
X plus y,
plus y.
right?
Sorry.
X plus y. Now let's think about this. 1x plus 1y. So can we write it as 1 choose 0 and 1 choose 1, right? Something like that. Okay, what about this? X plus y whole squared. 2 choose 0, x squared, plus 2 choose 1, or 2c1, xy, plus 2c2, y squared. X plus y whole cube is equal to 3c0 x cube plus 3c1 x squared y plus 3c2 xy squared plus 3c3 y cube, right? So what are these values? Look at this, 1c0, 1c1. Okay, I should have written that. 1, 1. What about this? 2c0, 1, 2c1, that is 2, 1. Next, 1, 3, 3, 1. 1, 4, 6, 4, 1. So on. Can you tell me what is this called? This is called Pascal's triangle. I mean, you can write something like this, or maybe something like this: 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So if you look at this, 6 is 3 plus 3, 4 is 1 plus 3, right? 4 is 1 plus 3, 3 is 1 plus 2, right? Make sense? So this is called Pascal's triangle. Pascal's triangle. If you just look at all these coefficients, right? If you get all these coefficients and construct a triangle, that's called Pascal's triangle. So similarly, x plus y whole power n is nc0 x power n plus nc1 x power n minus 1 y, nc2 x power n minus 2 y squared, so on. Keep doing this until you get ncn y power n. And here each coefficient, that is called the binomial coefficient, because this is called the binomial theorem. There are two values here, right? X plus x and y whole power n. So this is called the expansion of this is called the binomial theorem. And each coefficient here, n choose r, right? NCR, that is called the binomial coefficient. And these coefficients will make this Pascal's triangle. And Pascal's triangle, or these binomial coefficients, as we said, right, in a lot of applications. I also said it is same as R-sized subset, or R bits are ones. See, it occurs in a lot of places. So it's one of the most powerful combinatorial objects. So, you know, permutations is very famous, right? Permutations is used a lot. Similarly, combinations, this is called combinations. They are used a lot. Subsets are used a lot. So now you know that combinations and subsets are very related, right? So if you think about this, now look at this. Let's set x and y is equal to 1. 1 plus 1 whole power n is equal to 2 power n is equal to n choose 0, n choose 1, n choose 2, so on up till n choose n. That's a beautiful formula, right? So what is this? Zero-sized subsets of n. Total number of one-sized subsets of n. Total number of two-sized subsets of n. So on up till total number of n-sized subsets of n elements. If you add all these things, you should get total number of subsets of a set of n elements. And what is it? 2 power n. And you know 2 power n is the number of elements in the power set. That is the set of subsets of a set is a power set. Power set has 2 power elements. See, all these are related. Combinatorics, sets, right? Functions, and a lot of these ideas are related. Anyway, so let's move forward. So just some motivation, okay? Let's go to subproblem. Now you know that C of ij is I choose j, I see j, such that j shouldn't be greater than 0. J shouldn't be greater than I. J is upper bounded by I, and j is lower bounded by 0. If j is greater than I, we consider that as 0. But in this subproblem, we don't even consider it, okay? But mathematically, if j is greater than I see j for j greater than I is considered as 0, okay? We are interested in computing and choose R. So the idea is simple. I mean, you can prove this rigorously. I choose j, right? I see j is equal to I factorial by j factorial times I minus j factorial. So similarly, write the formula for this, and add everything. And you can show that I see j is equal to I minus 1 c j minus 1 plus I minus 1 cg. Okay, we will not go into all these details, proving and all that, but remember this. So you need to remember this. N choose R is equal to N minus 1 choose R plus N minus 1 choose R minus 1. This is a solid formula, very important formula, right? Used in Pascal's triangle, and a lot of other places. Okay, now the base case is 1. And how do we get 1? Because 100 choose 0 is 1. 100 choose 100 is 1. So similarly, I choose 0 is 1. I choose I is 1. Make sense? So in the Pascal triangle, that is the reason all these will be 1s. And all these will be 1s. Right? The entire, the first diagonal here and this another diagonal, the end diagonal here will be 1s for this reason. Okay, anyway, so let's move on. I choose j and j is upper bounded by I. What does that mean? Now, if you consider, say, I is equal to 10 here, so this is I, this is j, right? So j can only be up till this point. You cannot define j greater than I. Okay, so you are only filling the lower triangular portion of this matrix. Though you are defining the entire matrix, you're only filling or interested in the lower triangular portion. And how do you fill? Maybe you can fill row by row. Fill everything in this row and then fill everything in this row, so on. And the dependency is given this. Any cell here depends on the previous cell, right? See, this is ij, and you know that this is I minus 1 because it's the previous row, same column, previous row, previous column, right? So this is previous row, same column, previous row, previous column. Okay, so yeah, you can fill this table row by row if you want. Next, so here is the pseudocode. So take this as homework. Why do we have min of I comma r here, and why don't we have just I? Okay, so take this as homework. I don't want to go over all these details, but yeah, so this is the base case, right? The base case, and this is the recursion case. So in the loop, right, you consider the two loops, and then you can have base case or recursion case. You can also write it in different other ways, right? But we have just considered, one way of writing. But you can definitely optimize it further. Okay. Next, what is the complexity NR, right? Because you need to scan n rows and r columns, right? Next. So this is your Pascal's triangle. See, this is 0, C0, 1, C1, 1, C1, so 1, C0, 1, C1. So all these will be ones because they will be IC0. All these elements will be 1 because they will be of the form ICI. And IC0 is equal to ICI. Okay. And for that reason, in fact, every row is symmetric. Why? Because you know that NCR is equal to NCN minus R. Right? So it has to be symmetric. Every row is symmetric. Next, every element, how do you get it? This element plus this element. 20 plus 15 is 35. 15 plus 6 is 21. 35 plus 21 is 56. So on, right? Makes sense? So verify this. It takes time to analyze all these ideas, right? So verify all this. Next. Longest common substring. Okay. I give you two strings. String 1, X string, and Y string. Second string, Y string. The first string has M characters. The second string has N characters. Your aim is to find the longest common substring. First of all, can you tell me what is a substring?
A section, like a small section of consecutive characters in a string.
Right. A section of consecutive characters, a subarray, right? Okay. Now, what does the question ask? So you have two strings, X and Y. You want to find the longest common substring. So there can be multiple substrings. How many substrings are there for a given string? Suppose a given string has M characters. How many substrings are there?
M. Well, more than M. way more than M.
How many? See, for every ij, right? I less than or equal to j, that's a substring. Make sense? So
Yes.
M squared. I mean, if you get the exact number, I think it will be similar to the form M times M plus 1 by 2, something like that. Okay. So theta of M squared. So similarly, theta of N squared, substrings for Y, 1 to N, theta of N squared substrings. So what we want is, okay, among all these substrings of X, all these substrings of Y, consider the common substrings. Common substrings that are common to both these strings, and the longest of those common substrings. If you solve this in a naive way, I mean, think about it. You need to consider all these M squared and N squared substrings. You need to find the common substrings, and longest is not a big deal. It's a scan, but right? It takes a lot of effort, Okay, so is there a faster way to solve this problem? Right? So let's try, let's follow in this style, right? Subproblem. What is a subproblem? Let's consider this as the subproblem. L of ij is the length of the longest common suffix between two strings. First I characters of the first string, first j characters of the second string. Okay, so this is your X, right? From 1 to I. This is your second string Y from 1 to J. I mean, they can be of different lengths here, but I'm right. So take the longest common suffix. What do you mean by a suffix? It is a subarray at the end position, right? Suffix of a string is any subarray that is at the end of a string. What is a prefix? Substring or subarray that is at the starting point of the array. That is the prefix. This is the prefix. This is the suffix. Right? So what you are saving here at L of I comma j is the longest common suffix between the first I characters of the first string and the first j characters of the second string. If there is no suffix, okay, you will write it as 0, right? The length is 0. But if there is a suffix, then you can write it as 1, 2, 3, whatever. It's a natural number, right? I mean, whole number, 0 or 1, 2, 3, so. Make sense? So we are storing suffixes. So our aim is to compute this max of L of 1 to M, 1 to N. I mean, we will probably understand this later. We are not interested in L of M comma N. See, this gives us suffix, right? The longest common suffix of the first string and second string. But that's not the aim. We are interested in longest common substring, right? Hence, we consider all possible values in this array and take the max of it. That's our aim. Okay. Anyway, I mean, we will come back to this probably later, but let's see the recurrence. What is the recurrence? The recurrence is something like this. And can you tell me why? Okay, so let's see a diagram, right? Maybe that will help us. So as I always say, so try to consider a subproblem, I mean, with I comma j, and try to find the dependency of that subproblem with respect to its neighbors. Neighbors, right? Okay, now consider the first substring, first string X and second string Y. So I will just write the indices here, okay, for simplicity. 1 to I, 1 to J. What you do is, so this is the subproblem, right? So L of I comma J. We want to compute the longest common suffix of these two, X of 1 to I and Y of 1 to J. Okay? What you do is this. Compare the last character of X here and the last character of Y substring here. So what are the last characters? Can you tell me what are the last characters? X of I and Y of J. So compare, right? Compare if they are same or not. So there are two results. They can be same or they can be different, correct? Only two results, two possible results. Suppose they are different. What does that tell you? Can you tell me if the last character of X substring and the last character of Y substring here are different, what does that imply? Can you tell me what is the longest common suffix between X of 1 to I and Y of 1 to J?
Would it be 0?
Why 0?
Because the suffixes are different.
Right. When the last character is 0, there is no suffix, right? There cannot be any common suffix. So the common suffix itself is 0. Right? When the last characters are different, suppose A, B, C and E, F, G, H, I. So what is the longest common suffix between these two strings?
Nothing.
0. I mean, length of it is 0. Okay. Next case. Suppose the last characters are same. Same. Then what? Then what? Suppose
Move
the
to
last
the left.
Then?
Then you move to the left and compare those.
Very good. So you know that the last characters are same. So the suffix length should be at least 1, right? At least 1. Because these two are same, at least 1. 1 plus recursively compute the remaining component. What is the remaining component? Find the longest common suffix of X of 1 to I minus 1, right? And similarly, Y of 1 to J minus 1. That's it.
But Professor, what if so in your example over there where you have ABC and then E, F, G, H, J, what if ABC was in the middle of Y? Wouldn't we miss that?
Oh, okay. So you're saying we
Like
want to
if
find
X
the
is,
common substring, right?
yeah.
No, yeah. So right now, do not worry about it. So right now, we are worrying about the suffix itself. We will show
Okay.
how to find the common substring using this matrix,
Okay. Got it. Okay, thank you.
right? So does this make sense? When it is
Yes.
same, it's at least 1 character. So 1 plus the remaining characters in X, remaining characters in Y. So that is first I minus 1 characters, first J minus 1 characters. So L of I minus 1, J minus 1, done. Is this clear?
Yes.
Oh, okay. So let's go back. So this is your recurrence, right? That means if the last characters match, then you do L of I minus 1, j minus 1 plus 1. If they do not match, then multiply this with 0, right? That means you get 0. Make sense? If the last characters match only, then it is L of I minus 1, j minus 1 plus 1. If the last characters do not match, then you are multiplying this value with 0. I mean, you could have just written it as 0, but this seems kind of, crisp. Okay. Now let's go to the base case. There should be a base case, right? For recursion, what's the base case? If I is equal to 0, that means there is no character in one of the strings. Or j is equal to 0, no character in the other second string. If there is no character in one of the strings, I mean, one of the strings is completely empty, then of course the suffix will be nothing, right? The length of the longest common suffix will be kind of 0. That's it. So that's your recurrence. Okay. Now, to answer Stacy's question, suppose you have this A, B, C, D, right? Say X here. Maybe then you have G, F, G, H, B, C, D, K, Z. Now we want to find the longest common substring between these two strings, right? What happens? So answer was ABC. So is it ABC? No, not ABC. BCD, right? BCD. 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 Okay, so what do we do here? See, there was a case where if we had considered up till this point, right, X to BCD, so this entire substring and this entire substring, we would have stored the value as 3. Remember? Why? Because the longest common suffix of these two substrings is 3. BCD and BCD matches here. So we would have stored, right, at some cell the value of 3. So what we do is at the end, once we have this entire L table, we scan all the cell values and take the max of all these cell values.
Okay, I see. Okay,
Right? For some cell, we would have stored this value.
I see.
So that is the idea. Make sense?
Yeah.
So the dependency is, this is L of ij. Ij, it depends on only one cell, L of I minus 1, j minus 1. Right? Only one cell. And algorithm, okay, so analyze this later. Right? It is easy to understand from the recurrence. Now, let's take a look at the example. So here is your example, L of ij. So we said the characters of X are from 1 to M and then Y 1 to N, correct? We also add a 0th row and 0th column. 0 means so there is no string for for X. There is no string for Y. So that is the meaning of 0th row and 0th column. Suppose you have 4 characters of Y, say 3 characters of Y and nothing in X. What happens? What is the longest common substring?
0.
0, because right? There is no common suffix, so it's 0. Common suffix itself is 0. So in the entire 0th row or 0th column, the answer is 0. Okay, now let's take a look at this. What happens here? So x of 1 and then y of 2. The characters match. So the answer is 1 plus, right? So this was, let's write it as L of 1 comma, what was it? 2 is equal to 1 plus L of what? If the characters match, you do 0 comma 1, right? What is 0 comma 1? So it depends on this, right? What is L of 0 comma 1? 0.
0.
0 is equal to 1. Hence the answer is 1. Make sense? So anyway, so try looking at this. What about this cell? T and T matches. So 1 plus the cell value. So if you, okay, if you had S here, then S matches. So it is 1 plus, like whatever the value will be here, something like that, right? Then it would be 1, then it would be 2 here. So something like that. So try to understand each and every cell value in this table. Okay. Next, the space is this. Okay, now one claim. This is not a DP as per our definition of DP. This is not a DP problem. Can you tell me why? Though we have all these 7-step process, right? We wrote recursion and recurrence, subproblem, everything. But as per our definition of DP, this is not a DP problem. This is not a DP algorithm. Can you tell me why?
Does it have to do with something? Hold on.
So how did we define DP? Overlapping subproblems. Do we have overlapping subproblems here?
Yeah, it has to do with something where we're not using saved solutions from the table.
Okay, suppose you're not using saved solutions. Suppose you're directly calling these functions, not saving them. Will that affect the time complexity? Okay, so let me give you the solution, right? So typically DP, you need to have overlapping subproblems. That means 2 or more cells on the read cells. Read cells should be 2 or more. But how many read cells are there here? 1. 1.
Oh, I see.
Just 1. And you can use a normal recursive function and still the complexity will not change, right? The complexity will not change. Make sense?
Yeah.
So this is why we say that this is not a DP, right? It is not reading from 2 or more cells. And so if you write a recursion tree for this dependency, you will see that there is no recomputation, right? There is no recomputation. So overlapping subproblems are not there. Hence, this is not a DP problem. But it looks very similar to a DP problem, right? But it's not DP. But still, we could use all that subproblem, recurrence, all those ideas. So that's why these subproblems and recurrences are not kind of patented by DP or whatever. Subproblems is a concept that is part of any recursive algorithm. any recursive algorithm, right, should have a subproblem, because recursive subproblems, that's the meaning of it, right? It's not only related to DP. So that is the reason for any kind of problem, you first need to think about the subproblem and then find the recursive relationship and then decide whether it is a DP or not, whether you want to use a table to store all those solutions or not, right? See, till this point we didn't know whether it was DP or not. Once you look at the recurrence, now you know that it's not a DP. I mean, you can call this as probably decrease and conquer, right? You're reducing the subproblem by one size, I minus 1, j minus 1, only, nothing else. There are no overlapping subproblems. You could have used a normal recursive algorithm here, right? Not a big deal. Probably you can also try writing a non-recursive version, right, without any overlapping subproblems. So this is not a DP problem or not a DP solution, okay? Anyway, so we will stop here. Do you have any questions? So we still have a lot more problems to cover, right? I mean, we will cover it in the next 2 sessions or so.